All right, hello everyone. This is Dr. Iskandar Zulkarnain. So we are now in Icoget, International Conference of Oil and Gas Technology, and you are in parallel session 2, room number 2. So the track for today's session is on production operations and optimization 1. So in this track, we'll be featuring 7 speakers who will be presenting, and I would like to remind the audience we will have a 15-minute presentation followed by 5 minutes, um, 10 minutes presentation, sorry, with 5 minutes Q&A. And following that, during the Q&A session, if you have any questions to ask to the presenter, you may use the live Q&A function to post your question. All right. And our first presenter coming up will be Mr. Edward Lawrence. He is from Schlumberger, and his paper will be on maintaining asset integrity and meeting nomination during transient operations using multi-phase dynamic flow simulation. So without further ado, we will hand over the floor to Mr. Edward.
Hi, good afternoon, everyone. My name is Edwin Lawrence. I'm a production engineer from Schlumberger, Malaysia. Today, I'm going to present a topic entitled Maintaining Asset Integrity and Meeting Nomination During Transient Operation Using Multi-Phase Dynamic Flow Simulation. I'd like to thank University Technology of Petronas and Schlumberger for the opportunity and allowing me to present today. This is my agenda for today. I'm going to present overview and project background, followed by problem statement, then problem solutions, result and discussion, and benefit and analysis. And at the end of the presentation, I will open the floor for Q&A. Coming into the overview and project background, the field is located approximately 150 km northeast of Kota Baru, and there are 6 pipelines coming from the wellhead platform into the central processing platform and into the separator. Once the liquid has been separated, the liquid will flow to the pump and separated into the FSO itself, and gas flow will flow to the compressor and then to the power generator. The fuel production rates are declining now, and in order to achieve the sales gas target, the operator plans to increase the production. Therefore, by how they're going to do it is they plan to reduce the platform pressure from high pressure to low pressure mode. With that huge differential pressure on upstream and at platform itself, the rates increases from the platform into the central processing platform. Reducing pressure from high pressure to low pressure, what kind of effects into the central processing facility? As I mentioned in the previous slides, the liquid will be increased when we reduce from high pressure to low pressure, and it will come with liquid surge into the platform itself. With liquid surge, it could cause flat trip vibration if high gas flow rates are above the flaring gas rates limit, and it could cause separator trip with high liquid surge into the separator, and it could cause pump trip when the high liquid surge are higher than the pump capacity. In the same time, the operator set this operation to run for 7 days, and the operators want to optimize on the transient operation time and minimize the cost. So these are the project background. We will go into the problem statement itself. So this discuss the technical challenges that encountered by the operator. Number 1, frequent facility tripping will occur in recent years when operation were performing, especially production ramp up at the satellite platform. Another challenge is the duration of planned transient operation took longer than expected and not optimized. The potential risks from these challenges are potential damage to the equipment, potential trip or unit shutdown, safety to personnel on board, and longer period for transient operation, which led to higher OPEX costs, which will cause potential loss to the operator in terms of OPEX and penalty if the operator is not meeting the nomination rates. Based on these two challenges, we in Schlumberger see there is opportunity to improve the operational excellence since traditionally no simulation desktop study was done prior to field implementation. Therefore, to tackle this problem, we use transient analysis, which utilize the multi-phase dynamic flow simulator called OGA, which we use OGA to run the transient analysis, and based from the outcome from the OGA analysis, the operator implemented our solution in the field, which I will describe in the later slide. In these slides, explain the workflow in addressing the challenges that we face. First, we will do data gathering. The first data is we took the production rate, followed by the pipeline and riser data, freight data, process equipment data, and environmental data. Next, we will do the model building. First is develop the basis of design report. Second is develop the OGA pipeline and integrated network models. With the models being built, then we will run the model validation. How we do that is we run the individual pipeline matching and integrated network matching by matching the model with the latest field data. When the model is validated, we will use to run the transient simulations by running different sensitivity on different pressure scenario from high pressure to low pressure, and sensitivity on the transient operation duration days. With finally analysis and recommendation, we will perform constraint check on the separator itself, the pump and the compressor constraint, propose mitigation, and then develop operating procedure to the operators itself. The next slide shows the steady state analysis. The steady state analysis shows the OGA simulated liquid flow rate, which is in blue color, aligned with the measured liquid flow rate from the field, which is in orange color. This is to show the model are matched with the field data result, and with this confidence, the model are able to use to run transient simulation. This slide shows the transient analysis result. This shows two results, base case and sensitivity tree. The base case shows the result of 5.5 bar pressure reduction in 1 hour. This is the typical standard operating procedure that based on the operator experience in order to reduce the pressure. It shows that using the base case, the pump liquid production rate will be over the pump capacity limit, which caused the pump to trip in the platform. Therefore, sensitivity are run based on different pressure scenario, and in sensitivity tree is based on 0.25 bar pressure reduction in 6 hours. The result shows that the liquid level, pump production rate, and the number of planned days are within the operating limit. Therefore, sensitivity tree are used or chosen to be implemented in the actual field production. And it can show that, and this shows the actual operation or actual result from the operation. And the operation result are comparable with the OGA result with the maximum liquid level, pump liquid production rates, and planned number of days. This shows the OGA result for the base case scenario, where on the left side, the liquid level in the separator went up to 900 mm of liquid level, And on the right side, the pump liquid production rates went above the pump capacity limit of 30,000 barrels of liquid production rate. So therefore, base case are not used in performing the actual scenario. And we use the sensitivity tree. So this slide shows the OGA result for pressure sensitivity in reducing the pressure from high pressure to low pressure at a rate of 0.25 bar for 6 hours. The product, on the top left side shows the pressure reduction is in step level, reducing step by step from higher pressure to lower pressure. And the bottom left corner shows you the liquid level, but does not go above the separator limit of 1800 mm. And the right side shows the liquid flow rate result does not go above the maximum pump capacity limit of 30,000 barrels. And this slide shows the result from the actual operation. It shows that the pressure, liquid level on the left side are comparable with the sensitivity tree from the OGA result. And the liquid flow rate on the right side shows the liquid flow rate does not go above the maximum pump capacity. Therefore, with the help of OGA simulation result, the operation went successfully. So these are the benefit analysis from the simulation itself. So based on the simulation, we're able to improve the standard operating procedure for network transient operation. Second, provide safeguarding assurance, especially in avoiding maintenance due to trip. Third, optimize the number of transient days in the platform itself. And fourth, optimize the OPEX cost, including the number of people on board and barge costs. With that, this is my final slide. I'd like to say thank you to Schlumberger and University Technology of Petronas for the opportunity and allowing me to present today. And to everyone, do stay safe with these current situations and take care. Now, I'd like to open the floor for Q&A session. Thank you.
All right. So, audience, if you may pose question to our speaker here, Mr. Edwin. All right. Okay. So, very interesting topic, Mr. Edwin. Thank you for your presentation. All right. So, from your presentation just now, I guess using this Olga software is a very critical part of the project, right? And then how do you quantify like the economic benefit of successfully modeling this effect? Yeah, Edwin, probably we cannot hear you. Yep. Okay, I think all right. Okay, so I guess yeah, it seems we cannot hear you. All right. Okay, so probably we are waiting for our speaker. It seems like we are experiencing some technical, right? Hopefully we can resolve that. Okay. Okay, all right. Mr. Edwin, I think it's okay. All right. We can post your response later on. All right. So we have our next presenter coming up, and okay. All right. So our next presenter coming up is Mr. Um, all right. So our next presenter coming up is Mr. Ibrahim Ismail. So his next paper will be on synthesize and screening effect uh, and screening the effect of reaction parameters of BA, SMA, COMA. I'm sorry, as per point the presence on the yield and viscosity of Malaysian crude oil. So Ibrahim hails from University Malaysia Pahang. Um, and without further ado, we will move on to his presentation.
Assalamu alaikum warahmatullah. I'm Ibrahim Ismail, PhD student at University Malaysia Pahang. Today I'm going to share with you a part from my research area, which is synthesis, characterization, and pre-evaluation of a novel care polymer as a point represents to improve the flowability of Malaysian crude oil. Today's presentation will outline these parts, production, background, methodology, result and discussion, latest is conclusion. First of all, let's start with the brief introduction of the issue of wax deposition. As most of us know that the crude oil is a complex mixture of different compounds contain like aspartame, propane, aromatics, and many other compounds. So when we transport the crude oil through the pipeline, especially in the cold area and subsea, the temperature will lose from the crude oil to the surrounding area until reach the point which is called as wax appearance temperature. At this point, the crystal wax start to precipitate on the inner wall of the pipeline and lead to many problems like block the pipeline. There are many different strategy to deal with this issue, like mechanical, chemical, thermal. The most common strategy is chemical strategy because of the low cost and time. So no need for time, no need to shut down the production in the oil field. The goal of the current research is to synthesize a novel polymer which working as a wax inhibitor in the crude oil pipeline. The background of wax deposition is started early in 1923 in the United States, but at the time this issue it was not much common because most of the production have been in the areas offshore, I mean onshore area. But in the beginning of 20th century, when the world moved to the oil to the offshore oil field, this issue is started to increase drastically. So we can see in the map the red spot represent many different area reported with the wax deposition issue. Issue associated to wax deposition in the crude oil pipeline. The most common one is obstruct and block the pipeline. Also can increase the viscosity of the crude oil. The common one also, or the important one, cost and technically challenging, other safety issues, disposal problem, and also production interruption and decrease in the production rate. This slide represents the material that I have used in this research. Going to the preparation method, the monomers behind electrolyte steel mediate maleic anhydride was polymerized using free radical polymerization. The reactor was occupied by thermometer and nitrogen gas lit. The parameter selection parameter was ranged for time for 4 hours to 12 hours. The temperature also from 60 to 120 degrees Celsius. And we used the benzoyl peroxide as initiator, ranged from 0.5 to 2.5. Also, we use a different mole ratio of monomers. At the end of the reaction, the solution kept to cool, and later on added methanol to precipitate the polymer. Later on, the polymer was washed by methanol 3 times and kept in the vacuum drying for 12 hours. And the last thing we get the light powder shape of polymer. For the result and discussion, the characterization of the synthesis, the polymer, we use the HNMR and FTIR to characterize this polymer. And from this characterization, we can conclude that the alkyne chain muties, methacrylate muties, and malic anhydride muties of the used monomer was presents in the this characterization, which lead to, or which conclude that the synthesis, the polymer was successfully synthesized. And this one in the HNMR, we can see the chemical structure of the prepared polymer. Going to the screening of the polymerization parameters, we take in consideration 4 different parameters. The first one is monomer ratio. We synthesized different polymers with different mole ratio, and we concluded that the equal mole ratio of used monomer gave the optimum condition of the yield. So which is 86 degree or percentage. Also, another conclusion, when we increase the mole ratio of the high molecular weight monomer, vinyl acrylate, we get also high yield, which is 84%. Going to the second factor, which is reaction temperature. When the temperature increased, from 60 to 100 degrees Celsius, the yield increased from 50 to 85%. After the 100 degrees Celsius, there was no more increase in the yield. Going to the third factor, which is concentration of the initiator. Also, the initiator increased when we increase the percentage of the initiator from 0.5 until reach 2. The optimum condition of the yield we get at 2 WT of the initiator. The yield was about 86%. For the effective reaction time, when the reaction time increased from 4 hours until reach 8 hours, the yield increased from 70 until reach to 90%. So the optimum condition we get for the reaction temperature was at 8 hours. 8 hours. So we can conclude that after 8 hours of reaction, the yield no longer increased over time, which is indicating that the polymerization process is completed after 8 hours of reaction. Going to the evaluation process, in the evaluation process, we evaluate the viscosity of the prepared polymer when we apply the prepared polymer with the crude oil. So in this figure, we can see that the most significant effective viscosity reduction observed when we apply BBD with the concentration of 1,500 ppm. So the degree of viscosity reduction we can see in this figure, the degree of viscosity reduction at the concentration of 1,500 ppm. The most significant reduction get is 87 degree at 5 degrees Celsius until which is 47 degree at 40 degrees Celsius. When the BBD disperses the crude oil molecules, the long chain of monomers can separate the oil miceless, decrease the friction, and prevent the combination of oil molecules. As a result, the viscosity of the crude oil will reduce. The other evaluation process is profene inhibition efficiency, or called as the BIE. We used the Goldfinger setup or the Goldfinger experiment to evaluate the BIE. The BIE evaluation shows that the synthesis of the polymer is highly capable to decrease the rate of wax deposition. with the range of 34 to 45 degree. We can see in these two figures. This one is the wax deposited on the gold finger. Also, when the poly BA-CoSMA was employed as a wax inhibitor at 5 degree, the maximum BIE was observed at 45.6% was obtained. So, in conclusion, we can conclude that a novel ballpoint depressants of vinylchloride, stearinmetacrylate co-MA malic anhydride was synthesized as a flow improver in the crude oil pipeline using free radical polymerization. From the FTIR and NMR data, it's observed that alkyne chain immunities, metacrylate immunities, and malic anhydride immunities are presented in the synthesis polymer. From the screening process, the optimum condition was 100 Celsius degree for the temperature, 8 hours of reaction time, 1.5 WT percentage of the concentration of monomer, and monomer ratio was 1 to 1 to 1 mole ratio. For in the Goldfinger experiment, the maximum BIE was obtained after applying the BBD at 5 degrees Celsius and 200 RPM. When the BBD was also applied, the crude oil at the crude oil at the concentration of 1,500 ppm, the viscosity of the crude oil reduced about 87% from 70 to 9.2 at temperature of 5 degrees Celsius. Therefore, the new synthesized BA-CoSMA polymer was successfully formulated to improve the flowability problem of the Malaysian crude oil. Thank you for your listening.
All right. So thank you, Mr. Ibrahim. So it seems like due to some technical, Mr. Ibrahim is not be able to take any question and answer session. So we will move on to the next presenter, which is also Mr. Ibrahim here. So his next paper is on optimization and modeling of reaction parameters on the yield of polymer additives as flow improvers for Malaysian crude oil using RSM CCD methodology. So I will hand the floor to Mr. Ibrahim. So let's hear it from him. Okay.
I'm Ibrahim Ismail, PhD student at University of Malaysia, Pahang. Today I'm going to share with you, apart from my research topic, which is optimization and modeling of reaction parameters on the yield of polymeric additives as flow improver for Malaysian crude oil using RSM-CCD methodology. Today's presentation will outline introduction, background wax deposition methodology, and result discussion, and latest is conclusion. Firstly, let's start with the brief introduction about the issue of wax deposition. This issue is increasing drastically all over the world. The reason for this issue happened because the temperature of the crude oil decreased below the point called wax appearance temperature, or WAT. At this point, the crystal wax starts to precipitate out of the crude oil and deposit it in the inner wall of the pipeline. The wax deposition lead to many issues like increase the crude oil viscosity, plug the pipeline, also and decrease the flow, decrease the production rate, and many other issues that put or overhead cost for or a facility and sometimes lead to facility abandonment. To solve this issue, there's many different strategy like mechanical, thermal, chemical. The most used strategy is the chemical used using pre-treatment with the polymeric additives, which now as ballpoint depressants or flow improver. This strategy used cost and saving time. So, for example, no need to shut down the whole oil field to solve the issue. Also using the design experiment software will procedures leading to decrease the number of experiments and offering knowledge about the direct adverse effect of the study variables and interaction effect. Using CCD, which is one design of RSM model, is ideally suited to delegate the operational variables in the variety of assessment by simplifying the number of design points and an accurate feature estimate to provide pertinent detail for the testing lack of fit. The issue of wax deposition. The issue of wax deposition is started in 1923 in the United States. This is the first appearance was in the United States. At the time, it was not much common because most of the production was onshore. But when the world moved to offshore oil production in beginning of 20th century, this issue is increasing drastically. As we can see from the data on the left side of my screen, data obtained from Web of Science and Scopus, see how much research is still in this issue until 2020, which is around more than 180 publications each year. In the experimental section, in this slide shows the material that we have used to synthesize a novel ballpoint depressants, which working as a wax inhibitor. In this study, we take in consideration three main factors during the synthesis process, which is reaction temperature, reaction time, and concentration of initiator. In the experimental setup, the three different monomers was dissolved in 250 ml Nick flask using 50 ml of toluene as a solvent and POB or benzoyl peroxide as initiator. The reactor was occupied by thermometer and also a nitrogen gas inlet. After the reaction completed, the solution was kept to cool and precipitated by adding methanol. Later on, the polymer was washed 3 times by methanol and kept in the vacuum dry for 12 hours. And finally, we get the white powder in the polymer shape. Result and discussion. As I mentioned previously, we used the central composite design to design the models and to get the model for the experimental condition. Using the following question to get the number of runs, and in this time we get around 20 runs. The reaction reaction parameters was arranged for the reaction time was 7 to 9 hours. Temperature was 90 to 110 degrees Celsius, and the concentration was from 1 to 2 WT%. Development of regression and model equation. This table shows the experimental design matrix for the prepared polymer with the coded and actual factors. This is the 20 runs that designed by CCD. The last two columns shows the observed and the predicted response. This is predicted by the software, and this one, the observed response, was obtained from the experimental data. Also, we can the most important thing we can observe from the table 4 is the R-square value. R-square we get around 96% for the R-square, which is 96% of the data was explained by the model, and just around 3% of the data or the model not explained. This is the final model equation in terms of actual factors. For the ANOVA test, we can conclude that the response quadratic model was significance because the p-value was less than 0.005, and regarding the lack of fit was good results also, which is not significance, not significant. For the analysis of response surface, we can see the interaction between the three different variables. In this figure, we can see the reaction between temperature and initiator concentration. The highest optimum value was obtained 92.71 at 100 degrees Celsius of temperature and 1.5 of initiator concentration at fixed time 8 hours. Also, here we can see the interaction between time and initiator concentration. Also has a positive interact The highest yield was obtained around 92.71%. But the most clearly positive interaction was obtained between the reaction time and reaction temperature, as we can see in this figure. So for the reaction, the yield increasing continue to increase with increasing the time, and also the reaction temperature continue to increasing until stay the same level after around 100 degrees Celsius or 102 degrees Celsius. The optimum condition for the interaction between the reaction temperature and reaction time was around 93.48% at the condition of 8 hours of reaction time, 100 degrees Celsius of temperature, and 1.5 of the concentration of initiator. For the optimization and validation, by applying the desirability function, the obtained response was 93.75, at the reaction time 8.1, reaction temperature 102 degrees Celsius, and initiator concentration was 1.57 WT percentage total monomers. At the optimum condition, the experimental validation was conducted in triplicate, and we concluded that the average of yield was for the experimental data was 93.20, and the predicted one was at the time is 93.75. So the error between the experimental and the predicted was just around 0.55, indicating that the quadratic regression model was valid and accurate in predicting the response or the yield. In conclusion, this study had investigated and optimizing the three reaction parameters: reaction time, reaction temperature, and initiator concentration for synthesizing novel ballpoint debris synths. The optimum condition were 1.8 for reaction time, 102 degrees Celsius for reaction temperature, and 1.75 WT percent for initiator concentration. The optimum yield was 93.20 percentage. Regression model for ANOVA revealed that R square value was 9696.9696, indicating that our model could explain about 96.96% of data heterogeneity, and just around 3% of the total variation were not explained by the model. The validation was performed using three replication condition, and the maximum average yield value was 93.75 compared with the predicted value. There's an error of around 0.55%, therefore indicating that the model is extremely significant, confirming a close agreement between the experimental value and the predicted of PA, COSMA, COMA yield value. Thank you for your listening. This is some reference that I have used in this presentation. Thank you.
All right. So thank you, Ibrahim. So Ibrahim will not be around to take the question. So we have here his co-author, which is Mr. Basim. Will be able to take the questions. So let me see if we have any. Yeah. So let me see if we have any questions posed by the audience. All right. So we have one question here, Basim. So probably you can explain to us what is the limitation of your research so far. Yeah,
Okay.
go ahead.
The limitation is synthesis and characterization of the novel ballpoint, and this novel ballpoint used as a wax inhibitor to reduce to improve the flowability of Malaysian crude oil, and also to reduce the wax deposition into the pipeline during transportation and also during the production, and because the problem is wax deposition when occurs at pipeline, especially at low temperatures.
So I guess this wax inhibition is quite an interesting topic and very relevant to our oil and gas industry here. So when you develop and synthesis this wax inhibitor, right, this PPD, do you have any chance to compare the performance with with the commercial ones?
We compared with the commercial one, but that one is not like our contribution in our study. So our contribution to synthesis a new BBD, because and already we compare with EVA, because the Petronas using EVA. So I think almost same improving, yeah, same performance.
Do you expect like any potential to commercialize your chemical here?
Sorry, brother, I don't understand your point.
Okay, so since you already developed this PPD, right, and then you already conducted some tests, right? Do you see in the future any potential to make this commercial?
Yeah, I think of course, because the chemical that we are using, it's not expensive as much as EVA, and also the one of the advantage is this tercopolymer have long alkyl chain of the polymer. That's why the BBD have very good performance as using as BBD.
All right. So my other question probably, have you had any chance, let's say, to communicate with Petronas with regards to your PPD here? So I mean, probably they might be interested, you know, in order to adopt your chemical.
Actually, we compare with the commercial, but as in the previous studies, we didn't use the Petronas wax inhibitor, and we didn't compare it with the tercopolymer. So, but when we see the result from the previous studies, so it's not. I mean, it's not too much. It's almost similar performance.
Okay, all right, yeah. So probably is I mean, I'm suggesting probably like a next a best move, next step forward. Probably you might want to engage with Petronas, and then probably you might want to offer your PPD here to
So
to be tested by them, you know. So if they are interested, probably they can adopt your chemical, and then there will be like some beneficial collaboration with your team.
yes, of course. So
Okay,
we will try. We will try.
all right. Okay, so yeah, very interesting. Okay, so I guess that's all the question we have for this paper, and I would like to move to the next presentation. So it happens that Mr. Basim is here, and the next paper will be presented by him.
Yes.
So okay, so since he's already here, so the next paper will be on application of a full factorial design um, to screen the factors influencing the wax deposition of Malaysian crude oil. So without further ado, we will move on to listen to his presentation. Okay.
Bismillah ar-Rahman ar-Rahim. My name is Basim Arabi. I am from University of Malaysia, Bahang. Today, inshallah, I will present a small part of my PhD research, which entitled Application of Full Factor Design to Screen the Factor Influencing the Wax Deposition of Malaysian Crude Oil. Presentation outline, which is consisting of introduction, methodology, result discussion, and conclusion. Let's start from introduction. Wax deposition in production pipeline and transportation tubing from the offshore to inshore is critical in the oil and gas industry due to low temperature condition. As you can see in this figure, the layout of the subsea pipeline and the cross section of the pipeline already plugged by the wax deposit. So what is the wax deposition? Wax deposition happens when the temperature of the crude oil drops down its wax appearance temperature. So the wax started to precipitate from the crude oil and started to aggregate it into the pipeline channel. The typical problem caused by the wax deposition included reduction or plugging of the pipework, increase the fluid viscosity, which leads to increase the pumping pressure, restartability issue caused by the wax gel strength, reduce operating efficiency and process upsets with interruption to production or shutdowns, costly and technically challenging removal, especially in deep water pipeline, disposal problem associated with the accumulated wax. Methodology. This slide shows us the list of the chemical that I use in my research, which is consisting of sabaco-polymer, silica dioxide, toluene, and methanol. Experimental setup for synthesis of the PPD copolymer. So this apparatus, which is consisting of a 3-neck flask, thermometer, condenser, and magnetic stirrer with hot plate, and nitrogen gas cylinder. Goldfinger analysis. Goldfinger apparatus have been used to evaluate the wax deposition of the crude oil as shown in figure 2. And the wax deposit was scrubbed off from the surface tube of the Goldfinger and then weighted to estimate the paraffin inhibition efficiency. Experimental design of experiment. The screen-off factor was carried out using full factor design to identify the best contributing factor in order to reduce the wax deposition and determine the interaction between the factors that have significant effect on the wax deposit. Table 2 shows us the values of factor examined in the FFD for lower and higher level. So we have 5 factors which are speed of rotation, Goldfinger temperature, experimental duration, inhibitor concentration, nanosilica concentration. Result and discussion. This slide shows us the screening model experimental data in accordance with the standard order. This design, which is consisting of 19 experimental run at different ranges, and our response, which is wax deposit, and the lowest wax deposit was 0.12 gram at standard number 12. Table 4, variance analysis ANOVA, which is show us that this model was significant and also all the factor is significant, and the interaction, the highest interaction of factors BC was 6%, and the lack of it was not significant. R square was 0.9975, which is can be clarified 99.75% by the model, and whereas only 0.25% not clarified by the model. The main and interaction impact of the variables. So this figure showing the tendency of the primary impact plots when the level factor is different. This plot showed the factor B plus, C minus, and D plus had the lowest amount of wax deposit compared with B minus, C plus, and D minus. The effect of factor on the wax deposit. The effect of rotation speed on the wax deposit has a critical role in reducing wax deposit. And we can see in figure 4 the physical appearance of wax deposit at rotation speed ranging from 100 RPM to 300 RPM, and the lowest amount of wax deposit was at 300 RPM, while the effect of Goldfinger temperature on the wax deposition, the temperature differential between the plug of the crude oil sample and the Goldfinger surface tends to produce more hard crude oil, and the wax deposit of the wax deposit was found to be thicker and rough at 5 Celsius, while at 10 Celsius was very soft and thinner. The effect of experimental duration on the wax deposition. Most deposits on the surface of the Goldfinger were found after 3 hours of experimenting in construct to 1 hour. The wax deposit seems to be stronger and in harsh sharp. And also wax deposition have been observed to increase with increasing the residence time. And the last one is effect of Saba-copolymer concentration blended with nanosilica concentration on the wax deposition. And the optimum concentration was found at 1,200 ppm of Saba-copolymer and 4,000 ppm of nanosilica. And it was not this concentration had a thinner layer and also has a crispy property, as you can see in figure 7. Interaction between factor on the wax deposit. So the significant impact contribution on the wax deposition was BC, which is the highest interaction, as you can see, followed by CD. So you can see the lowest wax deposit was C minus and D plus here in figure 8B was the lowest amount of wax deposit, around 0.4 gram. Conclusion, the production of the wax is very important in oil and gas industry because of the wax accumulation in the crude oil pipeline in the gold regime. The optimum condition for reducing the amount of wax deposit have been identified using FFD, which are 300 RPM, 10 Celsius, 1 hour, 1,200 ppm, and 400 ppm respectively, and the lowest amount of wax deposit was 0.12 gram at this condition. The variance analysis ANOVA has detected that value of R squared to be 0.9975, this presenting that this model is able to clarify 99.75 of the data variation. The Goldfinger temperature was observed that the most affecting factor of the wax deposition. Moreover, the interaction of BC, CD, and BD were the most significant interaction, which strongly contributed of the wax deposition. This is some reference that I used in my PhD research. Thank you for your listening and attention.
Okay, so thank you. Thank you, Basim. All right, very interesting. Right, so just wondering here, it seems like you and Ibrahim are coming from the same university. So what is the difference between your work and Basim and Ibrahim's work?
Actually, there's not. We are both of us. We are synthesis a novel Bohr point. Okay, a novel BBD. So the different is material. So Ibrahim, he using material. It's different. I mean different material. So and also for mind. So I try to addition of nanosilica because nanosilica one of the most important factor that can be reduced the wax deposition. That's why I make addition for nanosilica, and also in this paper I use FFD design, full factor design, to minimize the range of factor because we have 4 factors which are temperature and experimental duration, 5 factors, and concentration of Saba, and concentration of nanosilica, and also the rotation speed. So we don't know the range, the exact range that can be get laser wax deposition.
Okay, all right. So just now you mentioned that you are using this experimental design, and then there's a lot of attention, like other other work that are being done and using this method. All right. And then is there any particular reason you are using a full factorial design instead of a CCD design?
Okay, well, CCD design is using for optimizing the factors, okay? But the first, in our study, the first thing we are using OFAT technique. OFAT technique, which means like we are using one factor at the time, and the other factor keep it as fixed. So after OFAT, because the range of the OFAT it's very wide, and when, for example, the temperature around from 5 Celsius to 30 or 40 Celsius. So when we minimize the factor, how can we minimize by FFD? Okay. Also, because the OFAT, we cannot see the interaction between the factors. So we are using FFD. After FFD, we have optimized the factors. So we see what is the best contribution factor by FFD. So I think 2 factors, and then we optimize that factor to see what is the best contribution factor.
Okay, all right. And then probably we also are interested to see whether like it seems like your team here has developed some novel chemicals for this PPD, for this sweat inhibition, right? And then in your university, do you have the opportunity to test this using like actual reservoir condition?
Condition.
Mm-hmm.
Yes, we are using Goldfinger temperature, and that's why actually it's of course it's not as real reservoir, but we are using Goldfinger to see the factors, the range of factor. So, but it's not like the real field, of course.
I understand. Okay. So is there by any chance like you have like a flow loop setup in your lab?
No. Only Goldfinger.
I see. Okay.
Of course, it's more better. Yeah, this is what we have.
I see. Okay. All right. You know, there's a potential to collaborate. You see, because in our lab we happen to have this flow loop. So probably if you are interested, all right, there's a potential to do collaboration on this one. You can utilize the flow loop available in UTP. Yeah.
Inshallah.
Okay. All right. So I guess that's it for our Q&A. Thank you, Basim, for your time. All right, to respond to the Q&A. All right. So I guess we will move on to the next speaker. So our next speaker here is Mr. Aslam. So Aslam will be presenting his paper on relative injectivity change of carbon dioxide in sandstone due to salt precipitation and fines migration. So Mr. Aslam hails from UTP, and currently he is working on finishing his PhD study. So without further ado, we will pass the floor to Mr. Aslam. Okay.
Hi, I'm Muhammad Aslam, a researcher from University Technology Petronas. So for today's presentation, I would like to share our findings on a project titled Relative Injectivity Change of Carbon Dioxide in Sandstone due to salt precipitation and fines migration. For today's presentation, first I will explain on the background of the study. Then I will state the objective of this project. Then followed by we call the methodology, how we conducted the research. After that, I will explain the result and discussion of this research. And then lastly, I will conclude my presentation. Okay, moving on to the background of study. Okay, when we are injecting what we call the CO2 in a large volume for sequestration in saline aquifer, whether the CO2 is produced from the high CO2 gas field or maybe from other sources. This will trigger what we call injectivity-related issues such as substitution and fine migration. So these two mechanisms have been stated as what we call as the main mechanism due to reactive interaction between CO2, brine, and rock. Then when we due to the CO2 brine rock reaction, it creates carbonate in solution and also dissolved minerals. Then, however, when we are continuously injected the CO2, this particle will flow together and may plug in the wellbore, and they will somehow affect the CO2 injectivity. So, however, up to now, the previous studies are limited to the theoretical modeling without the experimental verification. That's why in this project, the aim is to evaluate the combined effect of substitution and fast migration on CO2 injectivity. So, and then the scope of study will be covering on the core flood experimental and the permeability change. So, in terms of methodology, so first, the sandstone rock samples have been saturated, and then after that, the initial rock permeability was measured by using the brine. Then, for the core flood experiment, we use the relative permeability system unit, which is available in this lab in UTP. So, and there are two what I call parameters that will vary during the experiment, which is the first one is the brine salinity, where the salinity varies from the 0 to 100,000 ppm. And then for the fine particles, we have was introduced into what I call into the core samples to what I call to represent the fine migration scenario. And then there are two types of particle size that we use, which is the first one is 0.05 micrometer, and the second one was 0.015 micrometer. And lastly, we measure the final permeability of the core sample. So and this table one summarizes the experimental condition. For example, in terms of injection pressure that we applied during the experiment, which is about 12.4 MPa, which is equivalent about 1,800 psi, and the temperature was set at 60 degrees Celsius. And then for this, for all experiment, we used the sandstone core samples with the average porosity of 20% and then the permeability of 185 millidarcies. For in terms of in order to represent a realistic CO2 sequestration scenario, we injected the CO2 saturated brine followed by supercritical CO2, and then the flow rate was injected at 2 cubic meter per minute. And then to saturate the core sample, we use sodium chloride, which is this type of salt was normally found in the most of the saline aquifer zone around the world. And then in terms of in order to determine what we call the CO2 injectivity, we use the method which is introduced by Sokama and Oyam and also Yusuf, where they derive the what we call relative injectivity change to represent what we call the CO2 injectivity. So which is this is what we call the percentage of difference between the final permeability and also the initial permeability. Okay, moving on to we call the result and discussion part. Okay, first we would like to explain on the effect of substitution on CO2 injectivity change. Okay, firstly, when we look at this diagram, you can see that when we are increasing the brine salinity from 0 to 100,000 ppm, there is an increasing growth of substitution on each sample as the brine salinity increase. And then the rising amount of substitution is actually supported by what we call the theory proposed by Price Mueller. And then as more precipitate salt appears, the cross flow area within the pore that is available for flow decreases. This has contributed to the lower injective value at higher brine salinity. And then, okay, this figure shows what I call the compared images of the various sandstone core samples after the CO2 injection series at different brine salinity. So we can see that in the first figure, which is on the left side, minimal change was observed on the face of the core saturated with the fresh water or at 0 ppm. However, a small amount of salt, which is indicated by the red arrows, started to precipitate when 6,000 ppm sodium chloride was used. And then for the concentrated with a higher salinity of 30,000 and 100,000 ppm, there are more salt is coming and precipitated on the injected phase of the core sample. And this is somehow has reduced what I call the cross flow area within the pore, and it is available for flow decreases. And then on the next effect, which is the combined effect of salt precipitation and fine migration. And from the figure, the trend shows that while keeping fine size and fine concentration constant, the increasing brine salinity, which gives a higher amount of salt precipitation, will induce higher injectivity impairment. A higher amount of precipitated salt increases the jamming ratio, and more fines will be prone to entrapment. And then when we use the 0.05 micrometer particles, it gives very little effect on the injectivity alteration. And this might be because of the particles are free to pass through even on the smallest pore throat. And on the other case, when we use the larger particle of 0.015 micrometer, it gives 3 times higher than salt precipitation effect over the whole brine salinity range explored. Okay, on the next, the RSC values we found that have shifted from 13.6% to a higher value of 29% for the sample with 0.05 micrometer and 0.015 micrometer fine particle. And then when we use the 0.05 micrometer particle, it results in piping occurrence due to jamming ratio less than 0.01, which will result in no or very low injectivity changes. However, when a larger particle of 0.05 particle were used, although the jamming ratio is similar at 0.01, larger fine sizes at similar concentration promotes greater surface deposition and also multi-particle blocking in the porous media during the supercritical CO2 injection, which leads to a higher injectivity impairment. So now to conclude our research, it was found that brine salinity had a significant influence on injectivity change of sandstone rock after being injected with supercritical CO2. And the next point is the injectivity decrease with increase in brine salinity. The increasing salt precipitation growth with increasing brine salinity was supported by images of the injected phase of the core samples after the CO2 injection series. And lastly, the fine migration augmented the injectivity impairment as compared to salt precipitation alone as the brine salinity increases. So it can induce up to 3-fold injectivity alteration when using larger particle size, possibly due to particle piping, plugging at a different jamming ratio. So with that, that's all for my presentation. So now I open the floor for the question and answer session. Thank you for everyone for listening to our presentation.
Okay, so thank you, Mr. Aslam. So very interesting presentation on his part. But unfortunately, due to technical reason, Mr. Aslam will not be able to join the Q&A session. So I would like to move on to the next speaker. So our next speaker for this session is Dr. Asia Nusaibah from University Technology Petronas. So she'll be presenting her paper on glutamate-based ionic liquids as methane hydride inhibitor, experimental and Cosmo RS study. So without further ado, let us welcome Dr. Asia to present her work.
Assalamu alaikum warahmatullahi wabarakatuh, and a very good morning to everyone. I am Asia Nusaibah Masri from University Technology Petronas. The title of my research presentation is Glutamate-based ionic liquids as methane hydride inhibitor, experimental and Cosmo RS study. On 20th April 2010, a deadly explosion has killed 11 men and caused 507 million liters of crude oil to pour into the Gulf of Mexico. A study claimed that the explosion is due to the gas hydrate plugging. Gas hydrate is solid crystalline compounds consist of gas entrapped in a lattice water network, where some of the common gases are methane, ethane, and carbon dioxide. The hydrate shall grow and agglomerate by time due to Due to the capillary attraction among the shell, it leads to plugging and total pipeline blockage, thus resulting to explosion due to high pressure trap. In total, there are 1,117 oil and gas rigs in offshore and land. Thus, without any mitigation, all of the rigs are exposed to potential of explosion. A typical practical method used to inhibit gas hydrate in industry is through the chemical injection in the gas stream. The chemical inhibitors are divided into thermodynamic and kinetic hydrate inhibitors, or so-called low-dosage hydrate inhibitor. From here on, I will call them THI and KHI respectively. The conventional THIs are methanol and ethylene glycol. They are usually utilized at high concentration in the range of 10 to 50 weight% as they are volatile, thus increasing the material and storage cost. Additionally, they are toxic, thus their release to the environment should be avoided. On the other hand, the conventional KHI are polyvinyl pyrrolidone, or PVP, and polyvinyl caprolactam, or PVCap. They are less effective in extreme condition over a deeper water pipeline, which usually has a lower temperature and higher pressure. Ionic liquids are organic salts comprised of cation and anion. They usually appear as liquid at ambient condition. Their application has attracted substantial attention of researchers thanks to their distinct properties such as environmental friendly, tunable properties, simple recovery process, high thermal and chemical stability. For the case of gas hydrate inhibitor, hydrophilic ionic liquids are preferred because the high hydrogen bonding interaction of the ionic liquids may interrupt the hydrate shell nucleation and growth by interacting with water molecules. Hence, it may inhibit the gas hydrate formation and agglomeration. In this work, we have utilized 3 amino acid-based ionic liquids, where the anion used is glutamate anion, and the cations used are 1-ethyl-3-methyl-imidazolium cation, 1-cyanopropyl-3-methyl-imidazolium cation, and 1-butyl-3-methyl-imidazolium cation. The combination of the 3 cations with anion lead to imim-GMT ionic liquid, CpMim-GMT ionic liquid, and BMIM-GMT ionic liquid. We use citarium high-pressure micro-DSC to evaluate the heat flow spectrum over time and temperature with the presence of methane gas, where 10 weight% of ionic liquid in water are used in a temperature range of 253 to 293 Kelvin at 5 pressure points. A baseline is also made using blank samples containing only water. The results are used to evaluate the ability of ionic liquids as THI and KHI. Figure 1 shows an example of the high-pressure micro-DSC spectrum. On the left side, the exothermic peaks, which are the positive peaks, represent the ice and hydrate formations. The onset time of the hydrate formation peak is taken as the induction time, and its average is calculated using equation 2 as shown. On the right side, the endothermic peaks, which are the negative peaks, represent the ice and hydrate dissociation. The offset temperature of hydrate dissociation peak is taken as the hydrate dissociation temperature and used to plot the hydrate aqueous liquid vapor equilibrium curve. From here on, I will call it as HLVE curve. The average dissociation temperature is calculated using equation 3 as shown. We compared the HLVE curve of gas hydrate in pure water with literature to validate the reliability of the experimental procedure. The result is shown in figure 2, where the result of this study is congruent with the literature. We have also developed a standard correlation equation associating the methane hydrate dissociation temperature with the pressure based on our result and literature for a pressure range of 2.9 to 72.3 megapascal. Then we have tabulated the experimental and calculated hydrate dissociation temperature using the equation as shown in table 1, where we are able to get a very low average absolute error at 0.339%. Figure 3 is the HLVE curve generated from the hydrate dissociation temperature in water and 10 weight% ionic liquids. Based on this figure, we can see that ionic liquids have shifted the HLVE curve towards left to lower temperature. Hence, they can function as THI for methane hydrate. We have also calculated the average dissociation temperature of methane hydrate when different ionic liquids are used as shown in table 2. This average dissociation temperature represents the THI ability of the ionic liquids. The results shows that IMIM-GMT shows highest dissociation followed by CPIM-GMT and BMIM-GMT. We have also tabulated the average induction time determined from the onset time of the methane hydrate formation peak, as shown in table 2. The average induction time is the time when the first methane hydrate was formed, and it represents the KHI ability of the ionic liquids. The result shows that CPMIM-GMT shows the highest induction time, followed by IMIM-GMT and BMIM-GMT. To understand the result, we use CosmoRS software to investigate the interaction of these ion liquids with water at the molecular level. The properties of the molecules are investigated through charge distribution histograms named sigma profile, which is shown in figure 5. The histogram can be evaluated quantitatively by dividing it into 3 regions, which are hydrogen bond donor region on the left, nonpolar region in the middle, and hydrogen bond acceptor region on the right. The red line at the bottom represents water molecules, where the peak on the left at the hydrogen bond donor region is corresponded to the hydrogen atoms, while the peak on the right at the hydrogen bond acceptor region is corresponded to the oxygen atom having electron valence. All ionic liquids line also have peaks on the right at the hydrogen bond acceptor region because of the glutamate anion having 4 oxygen atoms with electron valence. Additionally, CpMn-GMT has an extra peak at the same region due to the existence of the cyanic group at the end of the alkyl chain. This cyanic group has triple bond, and the nitrogen atom in the group has electron valence, where they can act as hydrogen bond acceptor group. In the middle of the spectrum at the nonpolar region, all ionic liquids have high peaks because of the existence of imidazolium ring and alkyl chains. However, the height of all peaks depend on the alkyl chain length. The highest peak is a pink line, which is BMIM-GMT with 4 carbon alkyl chain, while the lower green peak is IMIM-GMT with 2 carbon alkyl chain. The shape of the peak for CpMn-GMT at the nonpolar region is slightly different from the others due to the difference in the structure of cation, where the cyanic group exists at the end of its alkyl chain. For further understanding of the correlation between the molecular properties of ionic liquids with their performance as a THI, we plotted the area under the curve of the sigma profile as shown in figure 6a. Interestingly, green column, which is the area under the curve for non-polar region, show an increasing trend, which is in contrast with the trend of the average dissociation temperature, which indicate their THI behavior. This opposite trend can be attributed to the decrease in non-polarity of the ionic liquid, which subsequently increases their interaction with water, thus facilitating the destabilization of the hydrate cage. To further validate this claim, we evaluated the THI performance of various ionic liquids having 2 and 4 alkyl chains in cation from the literature as shown in figure 6b. And we can see that the trends are similar with the result obtained in this study. Additionally, we used the sigma plot of various ionic liquids having different anion to plot figure 7, which shows the correlation between the average induction time and the area under the curve for hydrogen bond acceptor region in the sigma profile. Hydrogen bond acceptor region is used as the anion plot, as the anion plot is located at that region. The result shows that a linear correlation pattern was observed with high correlation coefficient, where the higher the area under the curve, the higher the hydrogen bonding accepting ability of the anion, thereby increases their interaction with water molecules and reduces the hydrate nucleation information, hence higher average induction time achieved. In conclusion, we have successfully developed a standard HLVE curve of methane hydrate dissociation in pure water is using the combined data from this study and literature. Besides that, we found that IMIM-GMT shows highest thermodynamic hydrate inhibition ability represented by its average dissociation temperature, while CpMn-GMT shows highest kinetic hydrate inhibition ability represented by its average induction time. Based on the result of this study and literature, we found that the pattern or trend of THI performance follows the polarity properties of the ionic liquid, while the trend for the KHI performance follows the hydrogen bond accepting properties of the ionic liquid. That's all from me. Thank you.
All right, thank you, Dr. Asia, for interesting presentation. Okay, so we have question from our audience here. So question number 1, what is the difference in the working mechanism between a glutamate-based ionic liquid and conventional ionic liquid? Perhaps you can elaborate more on this.
Bismillahirrahmanirrahim. First of all, for the conventional ionic liquids, usually until now, the one that have been used is basically halide-based, which means the difference is in terms of anion. So we have, for example, mine, I have BMIM-GMT. So usually BMIM chloride, BMIM bromide, BMIM iodide. So in terms of the mechanism is supposed to be the same because it's both are ionic liquids. The difference is actually the anion itself. And why am I using glutamate? It's because the conventional such as halide base, bemium chloride, bemium bromide, bemium iodide, they are found to be toxic. So glutamate-based ionic liquids having glutamate as an ion are actually synthesized using glutamic acid, which is naturally found in abundance. So we claim that it is potentially non-toxic. However, we haven't shown the result for the toxicity yet.
Okay, understand. All right, and then the next question we have from our audience here is on the screening criteria. So, what is the screening criteria for selecting the glutamate-based ionic liquids?
Okay, so in theory, for gas hydrate formation, hydrate will form due to the existence of hydrogen bond. So in order to stop the hydrate nucleation or hydrate formation, we need to insert a chemical that will also have a hydrogen bonding interaction with water. Thus, it will disturb the nucleation structure, the structure itself. So it will stop the nucleation process. So what we did is actually we use COSMOS, the software, to check the ideal hydrogen bonding energy of actually around 100 to 200 ionic liquids. And then we compare with the conventional ionic liquids such as bemium chloride and then imine chloride. And then we found that glutamate-based ionic liquids, because they are anion are different, so they have higher hydrogen bonding energy compared to the chloride-based ionic liquids. So in theory, since it has higher hydrogen bonding energy, so it's supposed to have higher interaction with the water molecule in the gas hydrate. That's how we did the screening actually.
Understand. Okay, and then based on your current work right now, um, how far do you evaluate readiness of your team to let's say commercialize this product?
So to commercialize this product, I think the second step would be we have to test in a mixed condition. For now, we are using pure methane. So pure methane is very ideal condition, right? So I believe that we need to evaluate in terms of mixed gas situation, whether the result will be the same or not, and then we need to actually maybe try to communicate with any industry to test. Maybe they do have like a set of place that we can test our ionic liquid whether it's suitable or not actually.
I see. And then I think this is probably my last question. All right. So with regards to this methane hydrate, right? I mean, looking at your team facility in UTP, is there any interest for you to, let's say, study the mechanism, how it works at the pore scale? I mean, inside the reservoir.
For now, that is still under consideration actually. We need to study more. First of all, maybe we have to confirm we have to try with other mixed gas, and then maybe there are like some consideration actually to collaborate with others if because in UTP itself actually there are also some other lecturers that do have some setup which actually almost representing the real reservoir. So it's actually our second step. So we do have that consideration.
Okay, all right. So thank you, Dr. Asia, for your interesting presentation and also your response to Q&A. All right,
Thank
very
you.
appreciate. Okay, and then I believe we have come to the end of our session now, and Dr. Asia is the last of our presenter for this track. So I really appreciate the audience for staying put with us to the end. All right. I hope you have a wonderful session and uh, a very fruitful one. Okay. So I guess without further ado, we will end our session for today. Thank you very much. All right.